Dear colleagues and dear guests, it's 12 o'clock and we're beginning the panel session for the defense of the thesis by Andrey Mereshchenko. The thesis is submitted in conformity with the requirements for the academic degree of the candidate of chemical science. The specialization is 020009. The topic of the thesis is excited state chemistry of some halogenated compounds of certain elements. I would like to say that under the order issued by St. Petersburg State University on the 18th of April 2018, number 3405/1, I, Sergei Tonik, professor of the Department of General and Inorganic Chemistry, have been appointed the chairperson of this dissertation board. Now, I would like to introduce my colleagues. Professor Valentin Semyonov, Doctor of Physical and Mathematical Science. Professor Igor Smirnov, Doctor of Chemical Sciences. Professor Gennady Ryabtsev, Doctor of Physical and Mathematical Science of the Stepanov Institute of Physics of the National Academy of Science of Belarus. And Professor Pyotr Sennikov is attending the session via Skype. He is a doctor of chemical science. He works at the Institute of Chemistry of High Purity Substances of the Russian Academy of Science. Under the federal law, as of the 23rd of August 1996, number 127FZ, St. Petersburg State University is entitled to confer academic degrees. The corresponding order on the procedure of granting academic degrees at St. Petersburg State University was issued on the 1st of September 2016. And the current session of the dissertation board is held in accordance with this order. According to the above-mentioned order, the session of the dissertation board is valid, providing 2/3 of the appointed board members are present. The total number is not to be fewer than 4 people. The dissertation board consists of 5 people, 5 of which are present, including 1 person, Professor Sennikov, who is attending the defense remotely via Skype. Therefore, we have a quorum. And the agenda is as follows. The dissertation session should not exceed 2 hours. Number 1, the chairman's presentation about the documents submitted by the candidate for the degree and their conformity with the requirements. The chairman's reply to the questions about the documents posted on the website, if any. I'm ready to answer these questions if necessary. The candidate's presentation providing an overview and findings of the research, 20 minutes. Questions to the candidate regarding his presentation, no more than 2 minutes for each question. Reports on the thesis. The board members will be taking the floor in turns. No more than 10 minutes for each person. The chairman's report on the thesis. The candidate's comments about the report on the thesis and replies to the questions. I think that we will ask the candidate to provide his comments after each report on the thesis being read. Open discussion. The floor will be given to the non-board members of the audience. They can give a brief account of their ideas or ask questions about the research. No more than 5 minutes for each person. It is necessary to fill in the registration form and give their full name before the talk. Please give your full name, your position, and the university you work at. The candidates reply to the questions no more than 5 minutes. Presentation of the candidate's thesis supervisor will not be held, since the candidate's thesis supervisor cannot be present because he is at a conference now, so I will read out his report. After that, we'll have a 5-minute break before the open balloting on conferring and non-conferring the academic degree. The discussion is not broadcast, and I will ask all the non-board members to leave the room, since this is the general procedure for the discussion. And we are familiar with this procedure because this is common practice for the dissertation boards. Open balloting, vote counting and recording the results in the protocol. Making a decision on whether to confer or not to confer the academic degree. Candidates' closing speech, no more than 2 minutes. I think it is enough. Before proceeding with the agenda, I would like to ask you to switch off your mobile phones. Please make sure that your mobile phones are switched off. Thank you. The panel session of the dissertation board is being recorded and broadcast on the website of St. Petersburg State University and is being interpreted into English. Since we do not have any reports in English, the interpreting will be into English only. So let's start with our agenda. The thesis is submitted in conformity with the requirements for the academic degree of the candidate of chemical science. This specialization is 020009, chemistry of high energy. The topic is excited state chemistry of halogenated compounds of certain elements. The thesis was approved for the defense by order number 3405/1 on the 18th of April 2018. The dissertation board is set up according to the order issued on the 18th of April 2018, and I have already introduced you the board members. The candidate for the degree has submitted the following documents to the academic secretary: an application in the name of the rector of St. Petersburg State University with a request to examine the thesis. The application was submitted on the 25th of December 2017. Report of the supervisor, Professor Yuri Teverianovich. List of published works containing 18 items which describe the major research findings, including 18 academic papers that have been published in peer-reviewed journals recommended by the Ministry of the Russian Education and Science. A PhD diploma, specialization photochemistry. The diploma is translated into Russian and it has an apostille, therefore it's an official document. A copy of the rector's order issued on the 26th of December 2014, number 7905/1, confirming that the PhD degree awarded to Andrey Mereshchenko by Bowling Green University, the United States, on the 8th of August 2013, is acknowledged by St. Petersburg State University. Thesis in Russian and English, a printed version with a manuscript copyright and a digital copy. The thesis is downloaded on the website of St. Petersburg State University. The thesis formatting and reference list comply with the state standard GOST 7.0.4. The above-mentioned documents comply with Item 12 of Section 3 of the Order on the Procedure of Granting Academic Degrees at St. Petersburg State University. Now, I would like to give the floor to Andrey Mereshchenko, so you have 20 minutes. You are welcome.
Good afternoon, distinguished members of the Dissertation Board and attendees. My topic is excited state chemistry of simple halogenated compounds of certain elements. My dissertation focuses on ultrafast photochemistry of non-metal halogenated compounds and metal halide complexes. Non-metal halogenated compounds are really crucial for atmospheric photochemistry. In particular, polyhalogenated methods are produced by volcanoes and algae. The products of their photochemical reactions destroy the ozone layer. They also form hydrogen halides in the atmosphere. Metal complexes are crucial for science and technology. These complexes are in active use as photocatalyzers, major components of solar batteries, as well as anti-cancer drugs in photodynamic therapy. Apart from these, copper proteins such as plasticinin and umecinin participate in photosynthesis as electron transfer agents. The main goal of this work is to study the excited state dynamics and the photochemical mechanism of halogenated non-metal compounds and transition metal halides complexes to reveal the general patterns of excited state chemistry of halogenated compounds. In order to reach this goal, the following problems need to be solved. First off, to determine the main relaxation paths of the electronic excited states and to study ultrafast photochemistry of halogenated non-metal compounds and transitional metal halide complexes in gas phase and solution, to reveal the effect of solution on the reaction rates, to perform detailed theoretical study to explain the experimental results by quantum chemical methods. Our focus was on a range of halogenated non-metal compounds, such as polybromethanes, mixed halomethanes, boron and phosphorus bramides, and a range of transition metal halide complexes such as copper, platinum, and iridium. The dynamics of photoinduced processes of these complexes and compounds was studied in different environments upon different kinds of excitation. The major experimental method I used was transient absorption spectroscopy. The principle of this method is as follows. An impulsive excitation brings molecules into excited electronic states. Then their optical density changes. In other words, that's called transient absorption. It's detected by with a delayed probe pulse. An analytical signal here is the transient absorption as a function of the probing wavelength and a time delay. This 3D spectrum can be given as a transient absorption spectrum at different time delays or as several kinetic curves at different probing wavelengths. The physics of the transient absorption spectrum is as follows. Usually, transient absorption spectrum contains both positive and negative signals. Positive signals are reaction products or excited states. Negative signals arise due to the depopulation of the ground state bleach of parent molecules or induced emission. Analyzing the amplitudes and spectrum shapes of transient absorption, we can define the mechanism and the speed of photoinduced processes. In this part of my report, I'd like to focus on the photochemistry of halogenated non-metal compounds. We focused on the photochemistry of bromine containing compounds of carbon, boron, and phosphorus upon excitation into N-sigma antibonding electronic excited states. Here we witness carbon-bromine bond breaking, which resulted in the radical CH2 bromine and atom of bromine. These radicals recombine in the solvent cell, forming an isomer with the bond carbon, boron, boron. Then it faces thermal back isomerization back into the parent molecule with the time constant of 100 picoseconds. For the bromoform molecule in acetonitrile, we revealed that absorption of the photon results in the carbon-bromine bond breaking with the formation of a radical pair. It recombines in the solvent cage, forming an isomer with the bond carbon, boron, boron. The speed of back isomerization depends on the polarity of the solvent. The time constant of back isomerization is several microseconds in nonpolar cyclohexane and about 300 picoseconds in polar acetonitrile. It was revealed that a vibrationally excited isomer, which absorbs the visible spectrum band, is formed within first 30 femtoseconds, and then it decays with the formation of a radical pair. The time constant was about 90 femtoseconds. It was believed that the formation of isomers with the bond element halogen is only typical for polyhalogenated methanes. However, we revealed that halides of other nonmetals can also photoisomerize. They can form isomers with the bond boron, boron, bromine, and phosphorus, bromine, bromine. Here we see photochemical reactions of dibromethane molecules, bromoform molecules, boron, bromide molecules, and phosphorus. Excitation of these molecules into N-sigma antibonding electronic excited states results in element bromine bond breaking. The radicals can recombine or escape the solvent cage. Isomer is formed directly from the electronically excited parent molecule. When there is no water, spirits, or when there is no water or spirit, unsaturated or other unsaturated compounds, the main isomer relaxation path is a back isomerization into the parent molecule. The speed of back isomerization depends on the polarity of solvent. Polar solvents stabilize the energy. We also studied a range of polyhalogenated methanes, which contain different halogens. For CF2I2, it was found out that directly that photochemical isomerization comes directly from the electronically excited parent molecule. It results in a vibrationally excited molecular iodine. Upon excitation of the wavelengths of 2066 nanometers, there is a bond breaking. They can recombine and form an isomer of brom iodine. If the wavelength is 232 nanometers, two radical pairs appear. Their bond is carbon, iodine, bromine, and carbon, bromine, iodine. Here we showed how we could use quantum reaction to control the process. Here we see the bond breaking of non-metal halogen. Isomers have a bond of element halogen. They have a high reactive capacity and short lifetime. Isomers with the bond element halogen arise directly from the electronically excited non-metal halides, both in the solution and in the gas phase. Here I'd like to focus on the photochemistry of transition metal halide complexes. Here our focus was on monochloride complex in acetone nitro. The major relaxation path in the excited state is the internal conversion with the formation of a vibrationally excited complex, which is absorbed at short time delays. However, spectral analysis of transit absorptions at longer time delays revealed photochemical ionic dissociation with the formation of copper 2+ and chloride ion. The latter followed the radical mechanism. This also resulted in the photoreduction of copper 2 to copper 1. The photochemistry of copper 4 chloride and copper 4 bromide was studied upon excitation into all possible DD electronic states, with a charge transfer from a ligand to a metal. Upon excitation into DD electronic states, transit absorption bands coincide with the absorption of these complexes to the DD states. There were no photochemical reaction products here. The analysis of transit absorption spectra and kinetic curves allowed to determine their lifetime. It's 5 picoseconds for the highest energy state, 1 picosecond for mid-level energy state B1, and less than 200 femtoseconds for the lowest energy state. We explained this by the potential energy surfaces analysis that was done by quantum chemical methods. We found out that A1 and B1 states, orange and blue lines, do not intersect with ground electronic state, so their relaxation is adiabatic in a picosecond time span. Relaxation into the state E is non-adiabatic in a femtosecond time span. For copper 4 bromide in the excited states, the major relaxation pathway is the internal conversion. In the time life is 7 picoseconds for state A1, 5 picoseconds for state B1, and less than 200 femtoseconds for the state E. For the states A1 and B1, the relaxation is adiabatic, and for the state E, the relaxation is non-adiabatic. It goes through conical intersection. Upon excitation of copper-4 chloride complex into ligand-metal charge transfer electronic states at short times, we witnessed vibrationally excited DD electronic states. Here we had copper-3 chloride as the result of chemical reaction. The major relaxation pathway is the internal conversion into the vibrationally hot ground DD electronic state, and photodissociation, ionic photodissociation. Photochemistry of the copper-4 bromide complex upon excitation into ligand metal charge transfer electronic state is similar to that of copper-4 chloride. The major relaxation path here is the internal conversion. Transient absorption spectroscopy allowed to reveal that ionic dissociation products of copper-4 chloride complexes and copper-4 bromide complexes recombined into the initial complex at a sub-microsecond time scale. After the recombination includes the exchange of ligands. We also studied the photochemistry of platinum-6 chloride complex in acetone nitro upon excitation into ligand metal charge transfer electronic state. According to stationary photolysis, it was found out that the product here is a molecule of acetone nitro. It's a substitution reaction with chloride ion substituted by a acetone nitro molecule. We witnessed photoreduction to platinum-3 and oxidation of acetone nitro molecule. Platinum-6 bromide complex photochemistry is similar to that of platinum-6 chloride complex. The most long-living product here is the photosolventation product. Photochemical mechanism of this platinum includes fast internal conversion and dissociation of halide ligand and solventation. For iridium bromine 6, we studied the dynamics of the lowest energy DD excited state. Major relaxation pathway is the internal conversion into parent electronic state with a time constant of 350 picoseconds. This is much longer time in comparison than the lifetime of the lowest energy DD electronic state of the copper-4 chloride complex. Internal conversion in the iridium-6 bromide complex is adiabatic with no conical intersection. For copper-4 chloride and for bromide, the relaxation is non-adiabatic in conical intersection. Here we see major relaxation pathways of excited state metal halide complexes. Here the major relaxation pathway is the internal conversion. Lifetime of these states varies from several dozens of femtoseconds to several hundreds of picoseconds. Here the excitation does not result in any photochemical reactions. We found out that excitation of transition metals halide complexes into ligand metal charge transfer electronic state, the major relaxation pathway is the internal conversion through the lower line ligand to metal charge transfer and ligand field excited states. Here we have ion dissociation, comparing the nature of excited states of non-metal halogenated compounds and transition halide complexes. LMCT excitation in transition metal halide complexes can be somehow considered as an analog of non-metal halogen transitions in non-metal halogenated compounds. Excitation of compounds into those types of electronic states results in element halogen bond breaking. However, there are some distinct differences. Thus, photodissociation quantum yield of transition halide complexes is significantly less than that of non-metal halogenated compounds. Also, as a result of photodissociation, transition metal halide complexes are able to form both halogen atoms and halide ions, whereas non-metal halogenated compounds photochemically form halogen atoms and molecules. Additionally, only non-metal halogenated compounds are able to photoisomerize into the intermediates with element halogen-halogen bonds. Major conclusions are given on this slide. Here I'd like to finish my presentation. Thank you. Thank you. We now have time for question and answer sessions. Questions about the candidate's presentation. Are there any questions from the board members? Maybe the board members have some questions. I have two questions to ask. The first question is as follows. You studied photochemistry of non-metal halides. This showed the formation of isomers with the halogen-halogen bond. This is a popular topic in current studies. It's often described through a halogen bond. Is there any correlation between the phenomena you studied, the formation of this halogen-halogen bond in an excited state, and the formation of halogen bond, which is mostly typical for ground states in platinum complexes and many other complexes? Is there any connection here? Thank you for the question. They are similar, but I haven't reviewed any correlation here because of their structure. If we're talking about the halogen bond in transition metals, there we have the formation of a weak bond. It's a chain mechanism. Here we have several resonating structures. This bond is rather similar to, it's a stronger bond, and it's a disputable issue. It's partly ionic, partly I have one more question. When discussing photochemistry of halides, you said that the kinetics of bromoform reactions is different in polar and non-polar solvents. As polar solvent, you used acetone nitro. It's not only a polar solvent, it's also a donor of electrons. Can you explain why there is such a big difference in kinetics? Is it only due to kinetics, or is it due to these donor-acceptor reactions in an excited state? Thank you for your question. I didn't go deep into this issue. I didn't focus on it at all. I based my study on the internal coordinates of reaction between an isomer and the parent molecule. It was found, and this is something we can read in literature, these transition state is more polar than the isomer molecule. When the polarity of solvent is increasing, then this transit state energy is decreasing at a higher speed than the isomer energy because of the polarity differences. This is what I based my assumption on. Thank you for your answer. When designing the structure of the metal-non-metal reaction, you say that there were some resonating states. Are they due to the method of dynamic absorption that you used? You have a limited set of excitation paths. Is it your general conclusion? Do you understand what I meant to say? You state that metals have some excited electronic states. Your study focuses on the dynamic absorption, and there are some limitations upon excitation that you have in your study. We found absorption, the electronic absorption spectra. These bands coincide with certain changes, electronic changes into new electronic states. I understand your question. We are now trying to use some other methods, not only electronic spectroscopy. We are also trying to introduce the column explosion method. At the current stage of the study, we only use the spectroscopy. So you only revealed these resonating structures. To put that roughly, are there any other methods that you could have used? We only identified major relaxation pathways of excited electronic states. Are there any more questions? I have a question. I actually have two questions. The first one is about donor-acceptor relations. methods used by the candidate, such as spectroscopy. The study would benefit from them. If we develop this question further, could you tell me something about the role of solvents? When you spoke about metal complexes, you mentioned two solvents, water and acetyl nitrile. Water is not very typical as solvent. Could you comment upon that? Why did you choose these solvents? First, about the solvent for metal halide complexes.
Я бы сказал, здесь есть...
I'd like to focus on two issues to answer your question. When we're discussing the copper halide plus in methanol and acetylnitrile, we found out that the quantum output in methanol is higher than in acetylnitrile. I didn't mention that in my report today, but you can find that in my thesis. There I write about the use of water. If you add a couple of percent of water, it speeds up the internal conversion of DD, excited electronic states. The transfer of energy from an excited complex on the water is obvious there. How does that happen? The term they use for that is hydrogen bond assisted non-radiative decay. As I said, it's an energy transfer by the first of mechanism from an excited molecule onto the water molecule, and the excitation of water molecule into the second or third vibrationally hot ground electronic state. This is due to the presence of water. So it's hydrogen we are to blame here. I see. Thank you for your answer. And the second slide, it's about the relevance. You use the term quantum control of chemical reactions, and you use this term once further in your presentation. Can you explain what's meant by this term? What does this term imply? Here I imply a possibility to manage a chemical reaction by varying such properties of light as wavelength, power, the shape of a pulse, which leads to excitation. Analyzing the current state of the art in this field of knowledge, we are at the very beginning of our path. we can selectively break bonds, and this is something very promising in science. It has been practiced for a long time. Okay, I'm satisfied, thank you. Quantum control is a very beautiful term, isn't it? It is. Are there any more questions? I'm proceeding with the agenda. There have not been any external reports. So we are now turning to the reports of the board members. The floor is given to Professor Sennikov.
I really liked the thesis. However, I have quite a lot of questions after reading the thesis. One of them is connected with the donor acceptance interaction, but we have already asked this question. I really appreciate the experimental part of the thesis, and I like the experimental methods that he used. I believe it's a unique setup that he uses. And I believe it's the beginning of major work and of some future work that can be conducted in this area. As for the choice of the compounds that he studied, I would like to ask a question regarding this issue. So the question is as follows. According to the title of the thesis, the author could have chosen a large number of compounds. Since he uses unique experimental methods to study the compounds, and in the theoretical part, he states that some halogenated compounds have not been sufficiently studied before. But in the thesis, the author studies only some halogenated metal complexes and some non-metal halides. And he does not study lots of compounds with fluorine and so on. When he studies the ligand field electronic state, the scope of his research is wider, but however, some compounds are not within the scope of his research, so I would like the candidate to tell me why he chose particular compounds and ignored some of them. Is it possible to use your methods to study such compounds as bromine fluorine 3, nitrogen fluorine 3, and some others? This is my major question that I have in my report, and I will be glad to listen to his answer. In this thesis, we chose the compounds because we wanted to demonstrate the patterns, and we chose some compounds as specific examples. The major reasons for choosing these compounds are as follows. First of all, it is difficult to conduct experiments. For example, the state of aggregation at room temperature and the wavelengths, the absorption wavelengths, as well as the stability in the air. For example, some fluoride compounds are gases at room temperature, and they actively react with water vapors, which makes the experiment very difficult to conduct. The classical experiment for transient absorption is applicable for different solutions. The experiment that we conducted is a unique one, since it is highly difficult to study compounds in a gas form, because the pressure and the concentration are quite low. So it took us 2 weeks to get all the necessary spectra for studying the compounds. So, as I've already said, there are some difficulties with conducting the experiment. Furthermore, fluorides and chlorides of non-metals are usually absorbed in the ultraviolet spectrum, and in the classical experiment we have enough excitation energy starting from 250 nanometers. We can conduct an experiment using 230 nanometers, and it's difficult to use the wavelength of 210 nanometers, where fluorides and chlorides can absorb the spectrum. Speaking about the halogenated complexes which contain iodine, I would like to say that these compounds have been studied before. Therefore, we decided to disregard these compounds.
Металлов.
For halogenated metal complexes, I would like to say that the electron transition bands in cuprum complexes are in the visible range. Cobalt to nickel 2 compounds are characterized by DD states in the visible range, and they are characterized by legal to metal charge transfer in the ultraviolet band. Moreover, when we take organic solvents, the lower wavelength leads to a bigger signal from the solvent. Therefore, it's difficult to divide the signals between the signal of the solvent and the signal of the substance. These are the major reasons why we studied the particular compounds that you find in my thesis. Thank you for answering your question. You have provided a well-founded explanation. I think you should have included this explanation into the text of your thesis so that everybody understands that you did not choose the compounds at random. I also have 4 minor questions. I'm not going to read them out since they are posted on the website. Or shall I read them? I think the candidate should answer the questions, and they have already been asked. Okay, I will read them out. The other critical remarks are quite minor. In the thesis, you spoke about the formation of isomers of alkene halogenide and boron and phosphorus bromide with the non-metal halogen-halogen bond. How can you describe their structure, and how can you explain the differences in their chemical reactions? Please answer this question. Scott Reed and other authors have conducted some theoretical research of these isomers in terms of their structure. The electronic structure can be described by several resonance structures. These resonance structures include the covalent structure, which means the molecule of polyhalon metal with longer bonds and different other structures. According to Scott Reed, bromoform has a potential ability to to come into different reactions in solvents. Acetone nitroton had some percentage of water, and we identified that there was a reaction with water with the formation of the SH bromine 3. For some iodine compounds, we can say that they can come into reaction with propane with the formation of a double bond. How did you interpret the transient absorption spectrum? We interpreted the transient absorption spectra in two ways: comparison with the standard spectrum, for example, cuprum chlor 3, and we also compared our calculations with the quantum calculations. The next question is, how can you explain the difference in behavior of transitional metals when they get excited to different electronic states? When halogenated complexes of metals are excited into DD states, we do not see any changes in the electron position. When they're excited to the ligand to metal charge transfer, the charge is transferred and it leads to the bond breaking. And the last question is as follows. You have shown that the lifespans of the excited states are very small. How can you explain the reason here? The major reason here is as follows. The form of the potential energy surface. In one case, the relaxation path is according to the adiabatic mechanism without overlapping, and in the next case we see the overlapping. In dissociation, the form of the potential energy surface can have a minimum, and in this case we have an internal conversion. In another case, there is a dissociative surface of the potential energy, there is no minimum, and the bond becomes longer, therefore we have a dissociation. So I would like to say that this is a complete graduate research which studies the photochemical and photophysical chemistry of halogenated compounds. I would like to say that the research findings are reliable and all the research findings are validated. And it contributes to the study of excited electronic states. The research findings have been published in 18 journals, which proves that the research findings have been evaluated by the scientific community. So the thesis by Andrey Mereshchenko complies with the major requirements set forth in order as of the 1st of September 2016, 6821/1 on the procedure of granting academic degrees at St. Petersburg State University. And Andrey Mereshchenko can be awarded the academic degree of the candidate of chemical science. The specialization is 020009, high energy chemistry. Thank you. Now I give the floor to Professor Ryabtsev.
I'd like to begin by saying that The major contribution from my point of view as a physicist is the explanation and analysis of dynamic absorption spectra. It's a complex issue, and it was done on the basis, on the analysis of spectra. This was substantiated by mathematical calculations. There are no external reports. However, on the 16th of May this year, the candidate made a report at our university. There were members from the photochemistry lab present. There were many high-profile experts in photochemistry who came to listen to Mereshchenko's report. Their opinion of the study is very high. So the major question and interest is that the basic materials that you used are simple. However, the chemical processes they undergo are very complex. And I think that is your biggest achievement. All the process take place at picosecond and femtosecond levels. All other details are perhaps not as important. An important conclusion is that you try to systematize a lot of information. I'm from Belarus, and we regard doctoral studies as a qualification work. In our Center of Laser Research, we believe that your study conforms all the requirements to such degrees. As for the critical remarks, the first one is not that serious. My colleagues have the same opinion, and we heard it here today. This is about your titles of chapters. You should have used the word photochemistry, not chemistry. Photochemistry is a brand new branch of chemistry. It's not much of a question. It's just a remark and a recommendation. Talking about the methodology of your study. This is about photo-induced processes with charge transfer. The effectiveness of an adiabatic charge transfer depends on the polarity and temperature of the solvent used. This dependency is used in experiments to explain the effects of charge transfers. You discuss these processes a lot in your thesis. However, the experimental methods are not always explained thoroughly. You have already partly answered this question. Still, maybe you have something to add. My answer is this. In my study, I didn't focus that much on the effectiveness of charge transfer because that was experimentally difficult. Quantum outputs were of interest. Usually, they're in a femtosecond time span. I focused more on the nature and dynamics of relaxation. I focused more on the next reaction, on the following reaction. Our experiments were devoted more to the interpretation of the products of reaction that followed. Is that because it's difficult to work with a solvent? At short time spans, solvent gives strong signal, so it complicates the study. In gas phase, bromoform deassociates into radicals. Does either bromoform deassociate radically in solvent? Can it deassociate with the formation of other radicals in gas phase? Indeed, it was revealed that it can deassociate radically. The quantum output is small here. It's more important in the gas phase. According to the column explosion spectroscopy, this data was not provided in the dissertation. The bromine molecule can really appear as an outcome of the reaction. Photochemical processes in such complexes as cuprum chloride or platinum bromide are studied only upon direct excitation with a charge transfer. However, it would have been of interest to study photochemical processes in these complexes in DD excited states. For platinum bromide, the coefficients are low. They are found in the ultraviolet spectrum. For the DD state, there are only about 100 coefficients, whereas with the transfer charge excitation, we have about 1,000 coefficients. You state that upon the excitation of cuprum chloride 4 and cuprum bromide 4, upon radiation at the wavelengths of 2000 nanometers, internal conversion for the first two complexes takes the time of 200 femtoseconds, and in case of iridium bromide 6, it takes about 360 picoseconds.
So the higher the vibrational state is, the slower the process is. For the other compounds, we see the overlapping between the surfaces. And my last question is as follows.
It's just a minor remark. This is something that the candidate has taken into account. So the thesis of Andrey Mereshchenko, excited state chemistry of simple halogenated compounds of certain elements, compliance with all the major requirements, and the candidate can be awarded the degree of the candidate of chemical sciences, specialization high energy chemistry. It was interesting for me to read the thesis. Much has been said about the photochemical parts of the study. What I'd like to highlight is that quality work.
The thesis is devoted to photochemistry, but it is very close to radiation chemistry, since the compounds he studies are also used in different radiation technology. And I believe that the use of this radiation technology is very important, and we have to study the primary reactions in the system. With the decay leads to the formation of many different compounds, and we do not know anything about the primary compounds or about the excitation states. And from this point of view, the thesis is interesting for radiation chemistry as well, because it describes the primary reactions that happen in the system. As for the critical remarks, I would like to say that they are related to the experimental part. It would be interesting to understand the difference between the setups for studying nanosecond spectroscopy and femtosecond spectroscopy, because I don't think that these setups are very similar. And another question is as follows. I would like to ask about the concentration of the solvents that you used to study the photochemistry of cuprum compounds. I believe that you used some elements and compounds for the reduction of the compound. Please clarify the concentration that you used. I mean the concentration of the solvents. As far as I understand, tetraethanol ammonium was included in the solvent, and it can have an effect on the yield. But in general, I believe that the thesis fully complies with the major requirements set forth in order on the procedure of granting academic degrees at St. Petersburg State University, and Andrey Mereshchenko can be awarded the academic degree of the candidate of chemical science. The specialization is high energy chemistry. Now please answer the question. As for the setup for nanosecond spectroscopy, I agree that I should have given the layout in the thesis, but I decided to give it in the presentation. What's the difference between nanosecond and femtosecond spectroscopy? We have two impulses, and the time decay is related to different time for paths, and in nanosecond we use the impulse light, and in femtosecond we use the constant light. This is the main difference. As for the solutions makeup, these solutions included different compounds. We wanted to have less copper than tetraethanol metanium. This was our main idea, and the reactions that happen at longer time intervals, I mean the reactions between the excited complex and the solvent, happen quite slowly. Therefore, even if they take place, we do not have to study them. Thank you. Now the floor is given to Professor Semyonov. Please ask your questions about the thesis. First of all, I liked the thesis. And the main objective of the thesis was as follows: to find out the major patterns using a very simple system. And it means that this is not a candidate degree, but rather a doctoral degree, because it identifies the major patterns. But my extensive experience of working with spectral methods allows me to say that the thesis is very interesting. The dynamics of spectrography methods is a highly relevant study, because nowadays we do not have an adequate quantum theory. In other words, it's difficult to compare the dynamic models, and it's difficult to describe the dynamic model. We have to use mathematical calculations to describe it, and the candidate for the degree is set up a very challenging task in his thesis. I did not ask any questions after the presentation, because I was more interested in the questions that I have formulated in my report. So I would like to read out my critical remarks and my questions. Number one of the tasks that you have set up is as follows: to reveal the effect of the solution on the reaction rate, mechanisms and yields of subsequent competing photochemical and light-independent reactions of the compounds. For non-metal halides, the impact of the solution is described, and you used the effect of the polarity of the solvent on the rate of the back isomerization. However, you ignored some issues in your thesis. I mean, you did not pay enough attention to the effect of the solvent on the metal halides. And I believe that you have already given an answer to this question, because one of my colleagues has asked this question. The next question. I think one of my colleagues has asked this question, but still I am going to read it out. You have revealed that the excitation of the compounds to charge transfer electronic states leads to the element halogen bond breaking. However, the excitation to the ligand field electron state does not lead to any chemical reactions. How can you explain the differences in the reactivity of the electronic excited states? But it was one of the questions that you have already answered. And number 3, one of the major experimental method is the transient absorption spectroscopy. What other experimental methods apart from this can you use ultra-fast photochemistry of the compounds? Is it possible to identify the structure of the intermediates using experiments, not only quantum calculations? Could you please clarify this issue as well? Thank you for your critical remarks. We can say that there are some methods that can study the structure. For example, the diffraction scattering spectroscopy. the Coulomb explosion spectroscopy and ultra-fast spectroscopy. But these types of spectroscopy are much more difficult from the technological point of view, and I did not have an opportunity to conduct such experiments because I had some difficulties. For X-ray methods and for Coulomb explosion spectroscopy, you need specific equipment. For example,
Сложная интерпретация. Если вот есть статьи в литературе по
such as a linear accelerator. As for the other methods, I can say that we get a smaller concentration of intermediates. In the solution we have substances in the ground state and in the excited state. And this solution is isotropic. Therefore, it's difficult to identify the structure using structural methods. Therefore, it's not the major method that is used by the scientific community. I would like to add that these methods also require some further calculations. And besides, the compounds might decay before you start conducting the experiment. And I would like to add another point here. The signal is very low, and the yield of energy is higher. But if we pump the energy, then we have lots of photons, so it's difficult to say what we are measuring in this case. Would you like to ask a question? I would like to say that I have seen lots of misprints in the thesis, but I did not pay much attention to them. It happens, I understand. Probably you were in a hurry or something else. Yes, from the experimental point of view, you have conducted a large work. The thesis of Andrey Mereshchenko complies with the major requirements set forth in order number 6821/1 as of the 1st of September 2016 on the procedure of granting academic degrees at St. Petersburg State University. And Andrey Mereshchenko can be awarded the academic degree of the candidate of chemical sciences. The specialization is 020009 high energy chemistry. Now, thank you. I would like to express my own opinion.
First off, I'd like to say that the thesis complies with all the major up-to-date requirements. The major contribution I see is the focus on the kinetics and time spans, something which was almost non-existent in terms of the studies before. These short time spans are of huge interest. These femtosecond intervals for these compounds was something not studied at all. This is what comprises the novelty of the study. The study allowed us to have a look into these short time span. It allowed us to look into what happens in a molecule after excitation. This is the major contribution and novelty of Andrey Mereshchenko. This is why we call it a doctoral study. A lot has been said about the relevance for the study, and there is something you can read about the relevance in the report which was posted online. So my focus is on the critical remarks right now. For the data given in pictures 3.2 and 3.3, it was not quite clear for me which mathematical calculations you used to obtain spectral curves. These spectra are dirty, and here, to provide any evidence to prove something, you have to use clear mathematical models, especially because the bands correspond to certain products of photoreactions and their intermediates. The same is true about the statement you make on page 51. There you say the spectra of transition absorption, which you obtained a result of global spectral analysis.
The curves were smoothed using specific software. The global data analysis is a specific term. It analyzes the whole range of data without smoothing and without approximation. It's a function on the time and on the time decay. We use a specific kinetic model, for example, a series of subsequent reactions, and we approximate the experimental models received with this model. And the result, the spectrum that we have received, is the result of approximation, and they are given without any smoothing. This is the total amount. In the first column, I show the wavelength. The rows are time decays. At the crossing, we have transient absorption. We also include the curve for group rates and the experimental model. And therefore, we have an approximation. Thank you for your clarification, but I think you should have described this in detail in the experimental part of your thesis. And
my second remark concerns the structure of the study. I believe that in section that focuses on data analysis, there are 3 pages with of theory. This is something that you should have included into the theoretical chapter of the dissertation, into the literary review. Page 140. The kinetic data is analyzed by Pauli exponential analysis. Here, the contribution of each component is important, if you use more than one, of course. Unfortunately, you haven't provided any explanation on the contribution of each component in the dissertation. I accept these critical remarks. I find it important too. On page 23, in the equation, stoichiometry is not right.
These equations are schematics, and it is connected with the fact that the structure of some intermediates is not identified. We do not have exact data about the specific intermediate and about the specific compounds that were used. But you should have said that we used approximation, since we do not have a specific knowledge about the product of reactions.
There were some other inaccuracies in the thesis. Page 7. Experimental data are confirmed by quantum chemical calculations. This is something impossible. You should have used a reversed order of words. An experiment shows that your calculations were right. Page 43. Energy of vertical electronic transitions. Table 3.1. The data in the table is over-accurate. It's senseless. Page 44. There you mention scans of the potential energy surfaces. I don't really understand what you mean by the word scan. Is it some specific term that you used? You find this term in literature. You should have provided a definition. A scan is a dependency of energy of a molecule on a vibration wave along which relaxation takes place. It didn't take you much time to read out the definition. It only indicates that you should have provided that definition in the thesis. I accept that. I just wanted to show you one example. Here we see the coordinates of reactions. It's a typical scan. Relative energy of the molecule and the reaction coordinates. Reaction coordinates included several.
Валентин Георгиевич уже говорил о досадных опечатках, но меня очень...
There were some misprints. Some figures are lacking spectra. I used the version you uploaded on the SPB website. Table 3.2, 3.3, 3.4, and 3.5, as well as table 4.6. You didn't specify whether you used nanometers or anything else. Let me specify. I accept your remark. In general, I don't have any more critical remarks. The thesis complies with the major requirements. It has novelty. It's a cutting-edge study. The focus is broad. The study is of practical value. It provides the foundations for the use of halogenated compounds in modern science and technology. The thesis of Andrey Mereshchenko, excited state chemistry of simple halogenated compounds of certain elements, complies with the major requirements set forth in the relevant order on the procedure of granting degrees at St. Petersburg State University, and Andrey Mereshchenko can be awarded the academic degree. Specialization is high energy chemistry. Chairman, Professor Tunik. So we have finished the one more item of our agenda. Is there anything else that you would like to say about the critical remarks and recommendations provided by the board members? Indeed, I accept all the critical remarks, and in some points I hurried, which resulted in misprints in my thesis. At times, I didn't provide a thorough enough definition or a process flow of some of the chemical reactions. Major part of questions concerned my research findings about the influence of a solvent. So we spoke about the polarity of solvents and how that affects the dynamics of excited states. I also explained how excited states occur. I also spoke about relaxation pathways. Thank you. Now the floor can be given to non-board members for their reviews, remarks, recommendations. Is there anyone who would like to take the floor? Maybe there are some comments upon the topic or the presentation made by the candidate. Could you please introduce yourself, and then you're welcome to take the floor. Could you please come up to the microphone? The session is being recorded, so I kindly ask you to use the microphone. Allow me to introduce myself. I'm a representative of the Institute of Chemistry. I'm familiar with Mereshchenko's works. Today I had a chance to go deeper into his research attempts. We are also conducting research in this cutting-edge field of science, and it's a very promising field indeed, especially when it comes to photochemical reactions with large or small quantum yield. It's of huge value for us, and I'd like to thank Andrey Mereshchenko for his contribution. I hope we'll keep in touch and collaborate together in future. Thank you. Is there anyone else who'd like to take the floor? Please remember to introduce yourself. Mikhail Skripkin, Associate Professor of the Institute of Chemistry, St. Petersburg State University. I have been tracking Andrey Mereshchenko's academic activity. His specialization is high-energy chemistry. However, I suppose that his contribution into organic chemistry is invaluable as well. This study opens up new vistas for the research in this field. It's interesting to have a look at the electronic structure of metals and how relaxation pathways correlate. I believe this is something of interest from the point of view of coordination chemistry. Thank you for your remark. Any more non-board members willing to take the floor? Now I'm going to read the report of the thesis advisor. It's a thesis advisor by Professor Ilinovich, the thesis advisor by Andrey Mereshchenko. He writes that he started this study back in 2002. Back in those days, he was a student at the academic gymnasium at St. Petersburg State University. Then he enrolled in St. Petersburg State University, and he conducted research in molecular spectroscopy of salts of metals. Then he became a postgraduate student at Bowling Green University, the USA, and in 2013 he became PhD in photochemistry. This was considered equivalent to the degree of the candidate of science by SPBU Rector's order. In 2013, he returned back to the postdoctoral program to the Department of Laser Chemistry, and since then he has been working as an associate professor. He is active as a university professor. He conducts classes for SPBU students and postgraduates, and for school children from the SPBU Academic Gymnasium. He is an active participant in organizing committees of student Olympiads. He uses a wide range of up-to-date research methods. He is active in his teaching and academic activity, and active in his collaboration with Russian and international teams. Centers of Photochemical Science of Bowling Green University, with German universities and Swiss academic and research teams. He is a professional, has a broad outlook, and he's an expert in his field of science. The study he has submitted for research is a deep and robust piece of work. It has high practical value and can be applied, its results can be applied in many modern fields of science and technology. He has reported his research findings at many international scholarly events. Totally, he has published 28 papers in peer-reviewed journals. His index is over 9, and I believe that his study is a complete study, and it complies with the major requirements set in the relevant order on granting academic degrees at St. Petersburg State University, and Andrey Mereshchenko can be awarded the academic degree. Signed by Professor Kirinovich. It's now time for the Dissertation Board to discuss the issue of conferring and non-conferring the academic degree. Could you please switch off the broadcast? And non-board members are kindly required to leave the hall.
И сейчас можно пригласить будет тогда... Да, можно пригласить всех тех, кто пришел на заседание. Открытое, да. Это открытое голосование. Давайте тогда выключим, да? Пока я буду задавать вопросы всем.
Is the broadcast on? It's on. I put for vote the issue of non-conforming or confirming the academic degree for open balloting. Let me remind you that the decision is positive, provided half of the board members and no more than 3 board members have voted for conferring the degree according to the relevant order of St. Petersburg State University. Professor Semyonov, member of the Dissertation Board, the Department of Analytical Chemistry at St. Petersburg State University. What's your opinion? I'm voting for. I'm in favor of this dissertation, and I'm in favor of granting the academic degree of Doctor of Chemical Sciences. Professor Smirnov, member of the Dissertation Board, professor of the Department of Chemistry at St. Petersburg State University. What is your opinion? I am for granting the academic degree of the Doctor of Chemistry, the specialization High Energy Chemistry. Member of the Dissertation Board, Professor Ryabtsov, Doctor of Physics and Chemistry, the Institute of Physics named after Stepanov of the National Academy of Sciences, Belarus. What is your opinion? I'm also in favor of this dissertation. And I think that this thesis complies with all the major requirements that forth in the relevant order of St. Petersburg State University, and the candidate can be confirmed, can be awarded the academic degree. Professor Sennikov, member of the Dissertation Board from the Russian Academy of Sciences. What is your opinion? I believe that Andrey Mereshchenko can be awarded the academic degree of the candidate of chemical sciences. The specialization is 020009, high energy chemistry. Let me now give my opinion. I'm Professor Tunik, professor of the Department of General and Organic Chemistry of St. Petersburg State University. I believe that Andrey Mereshchenko can be awarded the academic degree of the candidate of chemical sciences. The specialization is 020009, high energy chemistry. Let's now count the votes. All the members of the dissertation board are voting for awarding the academic degree to Andrey Mereshchenko. So, colleagues and attendees, let me announce that 5 out of 5 board members have voted for, and we don't have anyone who has voted against or abstained from voting. Andrey Mereshchenko is awarded the academic degree of the candidate of the Doctor of Chemical Sciences, and his specialization is 020009, high energy chemistry. The closing speech of the candidate, distinguished members of the board, distinguished colleagues and attendees. I'd like to thank the board members for their willingness to participate in the session today. I'd like to thank you for your invaluable remarks and effective criticism. My special thank you is to Gennady Ivanovich, and because he made a journey from Belarus to join the session today. I'd like to thank my colleagues for their input during the discussion of my results. I mean the colleagues from the Institute of Chemistry, Mr. Panov, Kaczmirovsky, Ivanov, and others. I'd like to thank my colleagues from other Russian and foreign universities, the research team of Chikalin from the Institute of Spectroscopy of the Russian Academy of Sciences, the research team of Professor Prisnin from Novosibirsk State University. I'd like to thank Alexander Ternovsky and his research team from the Bowling Green University and his photochemical research group. I used the equipment to conduct much of my research. I'd like to thank the research teams from the German Center, DAISY. I also used the equipment to conduct my studies. I'd like to thank academic foundations which provide funding for my studies. I'd like to thank the Research Park of St. Petersburg State University. I used the equipment to conduct my research. I'd like to thank the G-Risk Foundation, which financed my trips to Germany. And a big thank you to my family and friends who have always been great support. My parents, my sister, and my wife. My grandma. I'd like to commemorate my belated granddad and grandmother who have always been supporting me and inspiring me to become a better version of myself. My granny would often ask me to tell her something about science, and she was the one who raised a scientist. My congratulations on the successful defense. I would like to thank one and all for their